Alrighty then, welcome back. Today I was planning on covering trees and graphs. I don't know if I'm gonna make it all in one session. Hopefully I will. Okay, so trees and graphs. Let's start with trees. Let me also. Okay, so what's a tree generally? Uh, in software engineering, a tree is a data structure. It's a hierarchical data structure that consists of nodes where it's organized of course, in a tree-like structure, and the top node is called the root, an inversion of definition, so to say, in which the top node is called the root. And then each node has 0 or more child nodes, and nodes without children are called leaf nodes, and each node is connected to its children edges. So trees and graphs might be, when it comes to interview questions, a bit more complex, at least for me. Yeah, searching a tree is more complicated than, for example, searching an array or a linked list. Also, when it comes to big O notations, the worst cases and the average cases times mile may vary widely, and we must evaluate every algorithm more structurally. Let's start with trees. Yeah, I already said trees. So, as I said, tree is a data structure which consists of nodes. And as I said already, we have a root node which has 0 or more child nodes. Each child node has 0 or more child nodes of its own. An interesting point regarding trees is that trees cannot contain cycles. Okay, the nodes may or may not be in a particular order. They may or may not have links to their parent nodes. All right, and there is also a division of trees, but in a way, the easiest way to structurally think of a node in case of trees is in this case. So we can have a node class which will have a string of name, other nodes that will act as children. And of course, you can also create a tree class that will wrap this node, and that's basically it. Now, when it comes to trees, there is a specific division of a tree, and we have in this specific division we have binary trees. Okay, we have binary trees, and binary trees is a tree in which each node has up to 2 children. Okay, each node has only up to 2 children, and not all trees are binary trees. All right, now we can also have binary search trees, which is just a binary tree in which every node fits a specific ordering property. For example, in which each child is smaller than the parent, or left descendants are less or equal than the number which is greater or equal than all the right descendants. All right, so binary search trees, as I already said, these are types of binary trees where each node follows a certain guide, a certain property that allows for specific and efficient searching, insertion, and I don't know, deletion operations. For example, we can have something like this, in which all the values in the left subtree need to be smaller than n. So here I need 5. We have a 6. We have a 5. We have a 7 here. I can continue with this. I can put a 3 here, and I'll put another 7. Okay, let's put this one to be 8. So now we can have 20 here, and here we will have a number that is smaller than 8. But that's the gist of it. That's the main logic. All right, I understand this. And more often than not, when we are given a tree question on interviews, we assume by default that it is a binary search tree. Okay. Again, we can have trees that are balanced or unbalanced. All right. Also, we can have now the difference between a balanced search tree and an unbalanced search tree is that we have faster searching, and most often than not, we can search in O log of n. So O log of n in balanced trees, and in unbalanced trees we can even hit on, which means that we need to hit each node one time. All right. What else do I have here? Oh, we have another division. We have so these are all subdivisions of search trees. You can also have complete binary trees. Complete binary trees, which are trees which every level of the tree is fully filled except for perhaps the last level. So how would this look? We have a node here, a node here, a node here, here, and here. Now that's my fault for not creating more space. But here, here. Now this wouldn't be a complete binary tree, because the level of the tree before it isn't filled. But if we have this, now this would be a complete binary tree. Of course, if we fill the tree, starting from left to right. All right. What else do I have? We also have something called a full binary tree. I haven't heard about this one before, but a full binary tree is a binary tree in which every node has either 0 or 2 children. No nodes with only one children exist. Okay. And then we have a perfect binary tree. It's a tree that is both full and complete, and all leaf nodes will be at the same level. So this would be a perfect binary tree. Now, there's something that was, for me at least, not very nice when I was on interviews for different positions, and this is binary tree traversals. So there are 3 types of traversals in binary trees. We can do it in order. In order, pre-order, and post-order. So let's talk about each of them specifically. Now, in order traversal means to visit. when we traverse through the binary tree, we need to visit first the left branch, then the current node, and then the right branch. So basically, if I have a binary tree, so this would start here, go here, and then go here. So this would be 1, this would be 2, and this would be 3. But keep in mind, this visits the whole branch, so not only one of the nodes, but the whole branch. So basically here, if you have more of these, we would hit this one first and this one second, which means this one would be hit third, and so on. But let's leave it here. Now the second one is pre-order traversal. Now, pre-order traversals will visit the current node before the child knows. So how is this working? This is the, oops, this is the first one. Then this is the second one, this is the third one. All right, and lastly, let's talk about post order. It does it like this, like this, like this. And post order traversals visit the current node after the child nodes. All right. So the current node will be visited after the child node. So we start here. This is the second one, and this is the third one. Okay. Enough about this. What else do I have here? What else do I have here? We could also mention a concept called binary heaps. So what's a binary heap? A binary heap is a specialized binary tree that satisfies certain properties. Basically meaning we have a complete binary tree, which means that all levels are possibly filled except the last. So something similar to what we have here. Something similar to what we have here. We have some certain heap properties, which based on the heap that we use, and we can use either min heap or max heap, which means that the value of each node will be less than or equal to its children, and the smallest value will be at the root. And max heap will, of course, do the inverse, in which the value of each node is greater than or equal to its children, and the largest value is at the root. So there are some key features of heaps, basically that they are efficient for certain specific cases, such as implementing priority queues, but also that insertion and deletion operations have a time complexity of O log n, where n is the number of elements, and that the smallest or largest element, depending on the heap that we are using, is always at the root. Now, we can have something like this. 175. Here we can have 200. I don't know, here we can have 10 on the right node, and the left children of 10 will be, what could I put here? 110. Okay. So let's talk about some min heap operations. So we want to insert into a min heap, and we always start at inserting. Let me change this. Inserting at the element at the last available position, basically at the bottom. So let's say we want to insert, and then because this is a min heap and the 2 should be at the root, we need to fix the tree by swapping the new element with its parent until we find an appropriate spot for the element. Basically, this is called bubbling. So what will happen here is that we will replace 10 and 2. So 2 will be here and 10 will be here. And then, because this is not the correct place, we're also gonna bubble up the 2 here. And we're gonna put the 2 here, and we're gonna put the 8 now instead of the 2. And how will the new min heap look like? We are having 2. The left side isn't changing much, but the right side now has an 8, which was the root element, 110 here, and 10 here. Now, what is the time of this? It's also log n, where n is the number of nodes in the heap. And we can also extract the minimum element. And it's easy. It's always at the top. The minimum element is always the top element. But now we can ask ourselves a question: how can we remove the minimum element from the heap? So what can I do? I can remove it. So I'm killing the minimum element. It's 2. So after I kill it, I need to replace it with something, and I'm gonna replace it with. Let me just create it here. So after I kill it, I'm gonna replace it with the last element in the heap, and the last element in our case is 10. So I have a 10 here, a 100 here, an 8 here, 175, a 200, and 110. So now we need to swap the root element, because if this is a min heap, we know that 10 isn't the smallest element here. Because it is a min heap, we now need to replace and swap the minimum element with the last element in the heap. And then we need to bubble it down. So what happens now? We compare 10 with 8. And we realize that we need to do a little switcheroo. Then we put the 10 here. We compare the 10 with 100. It's smaller than 100, so this is the only swap that we need to do. Okay, so I think I'm gonna rename this mind map, and it's only gonna be trees. I'm just gonna put here in big bold letter trees, and I'm gonna create a new one for there. I'm gonna create a new one for graphs, but let's mention another concept here. A concept that I was not very introduced to it, and it's something called a tree, which is a prefix tree, which is a specialized tree-like data structure that is designed for efficient information. Thank you very much, Sadat. Hope you're having a great day as well, or great night. It must be pretty late where you live. Hope you have a great night. So, what is a tree? So it's a prefix tree. It's a specialized tree-like data structure designed for efficient information retrieval. It's particularly useful for handling strings and is often used in applications like autocomplete dictionary storage and spell checking. So how is a tree working? Each node represents a single character of a string, and a node can have multiple children, and each children can represent the next character in a string. And the root node is the starting point and does not contain any characters. So, okay, so this is mostly used in auto-completion. Wait, can I reduce this shit? Yeah, I can. So if I want to insert words, car, cat, and bat, so I have a root node. Oops. And I'm starting with a C. And then here I have an A on both sides, cat, and here on the right side I'm gonna have bat. And each path from the root all the way down to a leaf is a complete word. And what I can do, what we can do, what common operations are, it's insert a word, search for a word, we can prefix search, or delete a word. It's 2 a.m. here. Yeah. But I have internet connection problem. Hope you fix it. And I saw one of your streams the other day. You were doing something mobile development related. Wish you all the good, all the best, Senat. All the best in the new year, man. What the fuck? I'm trying to refresh my memory on some data structures for, not even for interviews, just so I know this shit. And I remember often I would come to interviews and they would ask me questions about trees and graphs, and trees and graphs are mostly concepts that you brush over, because especially when you just starting to look for jobs, no one is gonna ask you if you iOS developers are slapping, making a lot of dough, man. I have a friend, he's like killing it. So what I want, yeah, and so, sometimes you get lost. So I think this is a good thing to learn. Okay, so we have a tree, and we have characters are stored at each node, as I already said, and nodes are often used to indicate complete words. Yeah, I forgot. So we have these guys, which are the asterisk nodes, which indicate complete words. Which, if we have an asterisk under bat, it indicates that bat is complete. And the implementation, I don't know how I'll implement this. I hope I will implement this, but I believe almost every day I saw at least one. Oh yeah, lead code is great. I didn't use it a lot. I started using it again maybe a month or so ago. It has some nice questions, like really good ones. I haven't done a proper interview in maybe 4 years. I'm working in this company and I'm relatively happy. But I don't know, I think you should always keep yourself fresh, man. I'm really rusty. I'm really fucking rusty, man. So what was it? Yeah. So this is basically a specialized tree-like data structure. To be honest, I don't like theory. I would like to solve some problem, but let's do this. I don't know. The reason why I'm streaming is because I'm learning and I'm putting it out on the internet. I'm making myself responsible for myself by trying to stream to other people. Okay. Okay. So these are the trees. Do I have some trees questions? All right. So let's do some implementation. What do I have here? I have binary trees, binary search trees, binary tree traversals, trees. What was I doing? Yeah, this. Up. Will this open? It will open. Okay, let's do some questions. So, but I don't know what to do. I don't know. Okay, let's implement one of these guys. Let's implement one of these guys. Let's implement one of these guys. Let's implement a tree. How is this even? Markdown. Trees. Let's just say trees. And here I'm gonna start with some code. So this should be I have never implemented this guy. So first of all, I need to see how to implement a tree. First of all, how do you say a tree? Tree. How is this said? Am I saying it correctly? Try. How do you say this? How to pronounce?
Let's learn how to pronounce it. It originally comes from French, and in French it's said as trie. Yes, that's used in English also, in computer science.
Alright, it's three. Yeah, I also do this. I mean, the only reason why I'm streaming because I'm a lazy person. So when I'm streaming, when there are people watching, I know, like, people are watching. It's not only you learning something, maybe someone is there with you trying to learn some shit. And you need to respect people that are also giving their time, their precious time to you. So yeah, that's my reasoning behind streaming. So three. Okay. Let's. So what do I have here? What do I have here? So each node is a single character. No. Can I? I press shift and shift creates a new. All right. Each node is a single character. Oh, also I need end of word. Is this O or 0? This is so marker. EOW is end of word. Word marker. What else? What else? There are some functions that we need to implement, hopefully. Insert a word, search for a word. What else? Delete a word. How do I? No idea. Okay, so let's start with this. So, class tree. No, let's start with node. Init self. I fucking hate that I'm pressing enter every time because I'm holding shift and every time pressing enter by mistake. Okay, build everything up. Okay, so how? First of all, how can I tree? How to implement end of line marker? Tree data structure. Python. So what is he doing here? A tree of nodes connected by edges. Each node represents a character. Sometimes I suggest to learn C as a first. Yeah, C is great. C is fucking great. We learned it exclusively in university on my first year. Like everything we did in the first year, it was only done in C. Like file manipulations, okay, basic coding, learning about branching and conditionals and variables and stuff like that. But it's so good. It's expressive and it's easy because it's a pretty complex language, but the bare bones commands are relatively small, so you don't need to learn a lot. But yeah, let's just do. Okay, so it's child So what is he doing here? Why would he create? Okay, I'm not gonna create an array. I'm gonna do it like this. So I'm gonna create children. No, maybe an object. Self end of word is false. So this is an individual node. And of course, it's an uppercase F. So where are you? You are here. What I'm trying to do now is to implement an individual node. Okay, so this can be any letter, and of course a node can also be end of the line. You can have the property of being on a end of the line. All right. I'm a fucking idiot. Wait, I need to ask ChatGPT something. So yeah, I pressed enter again when holding shift. Okay, so what I need here is I created a node. Now I'm creating this guy. Oh man. I'm creating this guy. Def. Same thing, we need to initialize it. So I need to set because oh I forgot I have this on. So I need to set the root node, and the root node is just a root node. It should be empty. So self root. What am I typing here? Self root is what? A new tree node. Yeah, that as well. Yeah, once you have the ability to, I think the language is not important. I think the most important thing is the ability to think like a computer. Yeah, definitely, 100%, 100%. All right, so what I did here is I just created a root node. Now, insert self and word. So how is this working? How is this working? How is this working? So what would happen if I only had car and bat and I wanted to implement cat as well in this exact scenario? So I would compare by a string element. I would compare, wait, car and cat. But also why I don't have only one A, and then from this A I have both R and T swinging from it? No idea. I'm following a book. So how can I insert a word here? So I have a current. Okay, the current is the root. Most traversals are done like this in linked lists, in graphs, in trees. So now for character in word, yeah, for each character in the word that I want to add. So if the yes, oh, okay, I think I have it now. So basically, let me open my tablet again just quickly. So what happens now? I want to add, I don't have cat. Let's say I don't have cat. So I want to add cat. So I'm checking if the root node has any characters that sorry, the root node, and then I'm iterating through the cat for each string element for each character individually. So I'm iterating, and now I'm checking, okay, for C, does the children of the current element, and the current element is the root element. So if children of this guy have C, and we have a C right here, if we don't have it, we'll most probably do something else. But for now, I think I'm having this. I'm having this. Oh no. Oh no. Well, wait. Okay. So we have two options here. We iterated. We tried to insert a new word into tree, and I'm iterating through every character of it, and then I'm comparing if the character is not in current children, if it's not, then we need to create a new one. Current children for this character I'm sorry, is what? A tree node. And otherwise I'm gonna do, so this is if we don't have it. If I want to insert, if I have cat, bat, and car in my tree, and I want to insert, I don't know, a helicopter. So this is the correct way to do this. So what do I have here? Otherwise, if character is in the current children, so if I already have car and I'm inserting cat, and I'm comparing against the first letter, which is C, I already have it. So my next character will be the one that starts with this letter. So it's C. So I'm moving my current to this one. All right. And this is really simple. And what do we do when we come to the end? End of word end of word is true. Okay. I can also search, right? Self word. So I need to search for a word in the tree. Keep yourself up to trends then to be rusty, and I'm really rusty right now. So basically what I'm doing is I'm trying to implement a certain variant of a tree, which is called tree. I hope I said this. It's French. I don't know French. So it's called tree. Is it tree or tree? No idea. So I'm trying to implement this, and these are prefix trees, and basically they have, and they're not binary trees, and they can have n number of elements. They have characters that are stored at each node, and I can show you one example here. Where's my pen? Here's my pen. So basically, they are storing strings, and they're mostly used for autocompletes and predictions and stuff like this. So now we're actually trying to implement this guy. I'm implementing it, hopefully. Okay, so how does the search work? We have multiple words. Some of them have same base, same roots. I mean, all of them have same roots, but some of them a car and a cat have start from C, both of those. So what do I do here when I search? Let's say I search for cat. What do I do? Again, I'm setting the current to be the root. Basically what I'm doing is, if this is the root, I'm setting the current element to be equal to the root. So now when we traverse through the tree, I already have child elements here. So now if I'm searching for a cat, I'm looking, oh, do I have a C here? I have, here's a C. Okay, do I have an A here? I have both of these. I don't think this is visually implemented well. I think we should have only one. Let me just do this better. I think this should look like this. All right. So, okay, now I'm looking for A. Do I have an A? Yes, I do have an A. It's right here. And then I said, okay, do I have a T? I do have a T. All the way here, and sugar on top. We have the asterisk, and asterisk denotes something called end of line. So if you came here, if we come here and we hit the asterisk, we know that we came from the root CAT and we are searching for CAT here. Okay, we know that we found it. And that's the whole gist of it. It's a relatively simple data structure, hopefully. Hopefully, watch me fumble this and not be able to implement this. I'm following a book, not so closely though, but okay, for every character in the word. What am I? No, I'm for every character in the word. All right. Searching for a cat. I'm checking if character not if the character is not found in current children, returning false. Otherwise, I'm just moving the current to be the current with the character that we search against, and if we find it, current end of word. Return. Why is this not working? Because I need a return here. All right. No. Okay. So I have this. What else do I have here? What other method do I need to implement? That is the question. I can also have starts with, which is gonna have a prefix and it's gonna be the same basically. Self root for character in prefix if character not in current children, do the same, return false. Otherwise, current is equal to current children of the character, return true. This should be enough. So let's try to implement this. Tree insert cat. Oh no. Car and bat. Now let's tree. Why is this tree is not defined? Because I have an indentation error. All right. So let's see if we have cat tree search cat. This should be like here, and I'm also gonna search. Why am I creating a new line every time? Ah. Cat, bat, I don't know, helicopter. And if I run this, line 32 incomplete input. Where is incomplete input here? Ah, all right. I had a bug, but I fixed it. So cat is here, bat is here, helicopter is not here. Yeah, that's it. Seems pretty simple. So what is the complexity of this? I think it's if the length of the word we are searching is m, so it should be OFM for insert, OFM from search, and OFM for starts with, which is prefix matching. Now this is time complexity. The space complexity is okay. So we can have x amount of words. They can be in average, I don't know, epsilon amount of length. So it's gonna be OM times m. So this guy can consume a lot of memory. But yeah, that's it for now. These are the trees. So let's try to find an example. I need to read example from here. All right. So I'm gonna have a question here, and the question is gonna say markdown. Oops. So we need to create a minimal tree, and these are all the requirements given a sorted array with unique integer elements. Write an algorithm to create a binary search tree with minimal height. So first of all, let's go back to the drawing board. Let me open you. So what's a binary tree? A search tree. So a binary search tree can be balanced or unbalanced, right? Just a second. So binary search tree, it's a data structure used in computer science for organizing and storing data in a sorted manner. Each node has at most two children, a left child and a right child, with the left child containing values less than the parent node and the right child containing values greater than the parent node. Okay. All right, it has at most two children. So that's the only logic we have. But we need, in this case, we need, let me just, so this is going to be a question, minimal tree. So So in case we have this as an input, I'm just giving an example, just a second. So let's say I have 1, 2, 3, 4, 5, 6, 7. A tree with of a minimal height would be of the size log n, right? Because this optimizes the height. So if you have I don't know 8 elements, the max 7 elements, as in here. Okay. So how can I do this? How can I do this keeping in mind some of the binary search trees rules, such as all the left nodes should be smaller than the root node and all the right nodes should be greater than the root node? Okay. We can use a divide and conquer approach. So we're gonna get the middle array. That's gonna be the root. Then the left part of the array is gonna form the left subtree, and the right part is gonna form the right subtree. And most probably you're gonna need some recursion here to make this work. But this will ensure that the tree is as balanced as possible, which means it's gonna be the least amount of height. If we divide it every time, okay. So let's try to implement this code. Let's start with the tree node. Let's create a constructor. It's gonna have a value. Self value is gonna be value. Self. We're gonna have 2 children. Self left. It's none. Self right. None as well. Okay. Then let's create the minimum binary search tree, taking an array as an input. Okay, so if the array doesn't exist, I missed again. So if the array does not exist, I'm gonna return none. Otherwise, let's create the root node, and that's gonna be the length of the array divided by 2, and the root is gonna be this mid element. Now we need to create a recursive function for both left and right. Root left is what? I need to provide an array, and I'm gonna provide an array like this. So, oh shit, I forgot that my camera was on the whole time. So how? Minimal BST. Why is this not working? This should be recursive. It's not defined. Create minimal BST. All right. Why is this not defined? No, I don't want to debug it. I don't want to debug it, just run it, man. Why is this not defined? Create minimal BST. It's not defined, view problem. But it is defined, it's basically right here. It should be a recursive function, right? All right, let's do the in order traversal. Def in order traversal. If you remember from maybe an hour ago, I said that in order traversal starts from the left branch, goes to the current node, it then goes right. So if we have this guy working in order traversal, I hit the left again. I hit the left one, print node value, create an empty space for the end, in order traversal node right. This should be enough. Now let's create an array. Array is 1, 2, 3, 4, 5, 6, 7. Root is create minimum. All right. So okay. I messed up. I shouldn't. This wasn't supposed to be under the class. This was supposed to be separate like this. Okay, create minimal BST from the array. And then let's do in order traversal from the root. Will this work? No, I don't want to. How do I skip this? Yeah, it works. Cool. Cool. It works. Can I also print the tree? Let's do this. So def print tree. What do I need to take? I need to take the node. This is gonna be the root node. So if I have the root node, what I'm gonna do? Print tree. Print tree node left. Then I print the tree. I think I know, because here I need to know. I need to set the level. And here I'm gonna increase the level by 1. And now for the print itself, string node value, and here I'm gonna do node right. Wait. Maybe like this times level plus this. Print tree root. If this works, it doesn't work, of course. Doesn't work because I don't need a string here. I only need a string here. Okay. So if I do it like this, print nice. Okay, this is actually great. This is actually great. Oh, it's already one where I am. Guys, I'm really sorry. I need to end this right now. I'm gonna stream tomorrow. I think tomorrow I hope to do 3 or 4 hours. So if you want to study with me, join also tomorrow. See you in another one. Bye bye.